Hey everyone, welcome to the MacMillan Space Center. I'm Michael here on site at the unceded territory, the Musqueam, Squamish, and the Tsleil-Waututh, here with another round of our show, Ask an Astronomer, where we're going to go through all the space news that's happened in the last couple of weeks. We'll go live every second Thursday. And as always, we're here with our trusted astronomer, Rachel. Hey Rachel, how's it going?
Good. Yeah. Lots to talk about today.
Yeah, there was lots to talk about. So we're going to touch on a bunch of different subjects. We're going to talk about Mars in opposition. What is that? Then we're going to talk about spaghettification, like another crazy word. What is that? And then, of course, we have an event tonight about dark matter we can preview, and another amazing event that's happening out in space next week. So stick around to the end if you have any questions about any of that stuff or anything else you want to talk about. We even got some calls this morning about things that people saw up in the nighttime sky. So we'll take any and all of your questions. But let's start with this first one, Rachel, because I looked up at the sky the last couple nights, and up in the west, orbiting, over to the, in the east, orbiting over to the west, was a really bright red star, which of course is Mars. But why is it so bright, Rachel?
Because it's at opposition. And I feel like opposition is kind of a misnomer. It feels kind of like the opposite of what it's trying to say, but
Yeah.
basically it's our little Earth is in between the sun and Mars. So it's the closest approach that Mars and Earth make in its orbit. And that happens like around once every 26 months.
Right. So I
Yeah.
guess as the Earth orbits around, eventually we will get close to Mars. But this particular opposition is particularly exciting because not all the distances of our opposition are the same, right?
Exactly. Yeah. So there are times where it's closer than normal. So it's like closer or nearer opposition than other oppositions. And we call that a perihelic um, opposition. That's because Mars in the orbit around the sun, it's at the point where it's nearest to the sun.
Right.
So not
So,
only is it nearer to the sun, it's also near to us.
so say that word again, perihelion.
Yeah, perihelion. So peri being close to, and helion talking about Helios, the sun.
Yeah, exactly. So we're going to be throwing out lots of big words, but we'll go through them. And of course, if you have any questions, so Mars in opposition feels like very combative, but of course that means anything. Like would you say opposition for other planets as well? Like, could you say Venus in opposition and things like
For
that?
sure. Yeah, it's just a term to describe the positions of planets relative to us.
Okay, so Mars is opposition, really close to us. Let's take a look at some pictures, and then let's go right into this other big news story that came out on Sunday from Harvard, which is spaghettification and its relation to black holes. Now, that's just a fun word to say, but let's take a look at some Mars photos first.
So here, you should be able to see a little diagram of what it looks like for Mars to be at opposition. So we have Earth in the center, and we have Mars on the right, and the sun on the left-hand side. Now, for Mars on October 13th, that is when it reached its perihelic opposition, and it was only 63 million kilometers away
Only.
from Earth. Only 63 million, yeah. And of course, this can occur anywhere on Mars's orbit, as long as it is that nearest distance to Earth. And we had an opposition in 2003 that was particularly bright, particularly close. And that 2003 opposition was the closest approach in almost 60,000 years. So it happens once in a long time or a few years. And the next one's going to happen is 2035. So I would highly recommend going outside and trying to see if you can see that bright red dot in the nighttime sky. And the best time to go is at midnight, and you want to look due south at midnight.
That's really cool. Now, Rachel, of course, we've been talking a lot about Mars. We talked about Mars back in July, and we did talk about sort of like that window that, NASA launched off to Mars, and then also other countries launched off to Mars as well around that same window. So is this a coincidence? Are these things related? Because that window seems to be like where Earth is close to Mars, and are these two things coming together?
For sure, that's a really great point. And the answer is this is the cheapest way to send things to Mars, and that is what space agencies are all about. So when Earth and Mars are that close, it's a lot easier for us to send rocket ships, to send rovers, and eventually humans to Mars.
So right now, you can sort of picture on your diagram here is the Mars rover Perseverance somewhere in between there on its way to Mars.
Exactly. Yeah.
Amazing. So make sure to be checking us back out back in February. We're going to be doing lots of fun events around that landing of the Perseverance rover on Mars. But for now, let's get into the second big story of this week. So Harvard published this new paper about spaghettification. Rachel, I am getting kind of hungry. This is just after lunch, but what is spaghettification?
That's a great question. And maybe I'll go jump ahead to a really lovely picture of an astronaut getting stretched and undergoing spaghettification. So spaghettification happens when, if we imagine sending in some poor astronaut, hopefully who has volunteered to do this, and they go in feet first. And so because they go in feet first, the gravitational effects on his feet are pulling and stretching the astronaut, and it's affecting or pulling harder on its feet than on his head. So that's when you get kind of a differentiation of forces. So it's almost like a gradient going up this astronaut where you have stronger forces at your feet and less stronger forces at your head. And he gets stretched out into a long, thin noodle. And of course, astronomers are very clever when it comes to naming things, and we call it spaghettification.
So it's a very comfortable process, is what you're saying.
Well, yeah, if you like yoga, maybe you'll like that too.
It's true. I do like yoga. So tell us about like what. So we have known about spaghettification in the past. We have talked about it a bit when we talk about black holes. But what was this new discovery all about?
So this is really cool because we were able to see the last moments of a star being eaten by a supermassive black hole. And when I say being eaten, I really mean that it's undergoing that process of spaghettification. You can see stills of images of what that would look like as the star is getting devoured by this black hole. And the reason why this was really cool is because it was particularly bright and actually pretty close to Earth. And it's the nearest flare observed to date of this type of a star being eaten by a super hungry black hole. And so this happens when a star wanders a little bit too close to a black hole such as this one, and it gets ripped apart. And so this one was just 215 million light years. So it's a little bit further than the 65 million kilometers, but it is the closest flare recorded to date.
Wow, this is really cool. Now, of course, this term spaghettification was first really a theory, right? Like, it's not like as if like we had seen this before. So that what you're talking about, this is the first time that we've actually seen this happen?
With a star, it's the first time we've seen it with such detail because it's so close. Because normally we would have a lot of dust and debris that are clouding around and we won't be able to see into it. And so because it's so close, we're actually able to get a lot of information all the way across the electromagnetic spectrum. So things like in the optical and the radio, which we weren't really able to do before. And so it's almost kind of like this black hole is lifting the curtain of debris and dust and allowing us to see inside as it's having its meal.
Wow, amazing. So we do have some questions coming in. We do have a grade 5-6 class joining us from Richmond who've got lots of interesting questions. The first one that I think is really fun, and I think we should both tackle this one, Rachel, which is a very basic question, which is, what is space like? Now, this is going to be a challenge for each of us. You know, if you can describe what space is like in just like a sentence or two.
Sure. Well, yeah, it is kind of difficult because the closest I've been to space is my Zoom background here.
Yeah.
But I think that a good way of explaining it is that kind of overview effect. And so when you are doing EVAs or extravehicular activities outside of something like the space station, when you look down below your feet, there's nothing there. It's just blackness for as far as your eye can see and stars sprinkled around. And when you look at our Earth, you can see that it's kind of this blue marble floating in the middle of all that nothingness. And it's kind of both terrifying and also inspiring at the same time.
Yeah. So space is very big. It's very black, which means there's a lot of actual space to kind of like move through. But it is also really bright in the contrast that we see here, even under the black hole, and stars and blackness create a really wonderful contrast. But it is sort of like very big and expansive. And I like to think of space as everything. It is, when I talk about space, we talk about the universe, we are literally talking about everything, but there is so much unknown about space, which really excites me, which is why I love learning about it so much, because every time that we make these new discoveries, we are learning more about everything. And as we learn more about the universe, we inevitably learn more about us, because we are such a tiny little speck, you know, in that large cosmos. As you say, Rachel, that overview effect. Our planet is very fragile, but also very special. Let's go to another question from the grade 5-6 class. I think it was more of a personal question for you, Rachel. When did you start learning about space?
Ooh. I actually remember having a massive book that still had Pluto as a planet and a poster that's still up in my study that I should take down that has Pluto as a planet on this poster. But I started pretty young. I was always fascinated with space and looking up at the stars. And I always thought that they were really pretty, really beautiful. And then eventually I got more into math, and the way to combine math and physics and the beauty of the cosmos is through astronomy.
Sorry, I turned off your video, Rachel. I was just going to try to get you to stop sharing your screen there. You
No
can turn
problem.
back on your video. But yeah, that's a really wonderful story. Yeah, I was very similar to me. I remember I think it was a National Geographic book. I think it was called The Universe. And it was like really thick. And what was also really cool was that I had a subscription to National Geographic. Now, this is back in the 1980s, and there was a particular spacecraft that was going on a really cool journey through our solar system in the 1980s. Do you know which one I'm talking about, Rachel?
Yep, yeah. The Voyager missions.
Yeah. So
Yeah.
as Voyager, approached Jupiter, we like this National Geographic was like, see Jupiter up close for the first time. And then like a few years later, Saturn. And then a few years later, Uranus. Like stretched out all through the 80s. I think 1980 was Jupiter, and then like like Neptune was like 1989. So basically, all through my childhood was like these National Geographics that told us all about the solar system. I've been fascinated with space ever since. Let's keep going with some of these questions from this class. Amazing that you've joined here. Tell us what school you're from. And how long does Earth take to orbit the sun? That's a good
Uh,
one.
so I actually grew up not that far from Richmond. I grew up in White Rock in South Surrey, and I went to a high school called Elgin Park Secondary, and then I ended up going to UBC a little bit after that to do my undergraduate degree.
There we go.
And to answer your question about how long it takes, we define 1 year as one trip of Earth around the sun. So in normal terms, we would say that's 365 days. If you're an astronomer, then you would say it's 365 and a quarter days.
Right. And of course, since we are talking about orbits, and you did talk about sort of like the Mars opposition, all planets have different orbits, right?
Exactly, yeah. And there's things like gravitational effects, like planets like Jupiter are really massive, so they have a stronger gravitational pull that can affect orbits. And also, the orbits aren't perfectly circular, they're more like ellipses or like squished ovals. And yeah, and they all have different times or different years and lengths of times that it takes to go around the sun. And usually we say it in terms of Earth years because that's the most familiar unit of time that we have.
Right. Yeah. It is very Earth-centric to say that, but so far we haven't found any other intelligent life that can call us out on that. But at some point they probably will. They're just like, you guys talk about Earth quite a lot. Uh, another question from the class: how far away is the International Space Station? Of course, the only place so far that we are sending humans for now. But how far away is it?
So it's in something called a low Earth orbit or an LEO. And it's around 400 kilometers straight up from the ground, orbiting up in the sky. And I think that's really cool that astronauts on the ISS get to experience something called microgravity. So it's not quite zero gravity, but it's microgravity in that they have things like weightlessness, like the kind of feeling that you have when your stomach shoots up and you're on a roller coaster. But I think that'd be really cool to go on the ISS 400 kilometers up.
Amazingly. And in a follow-up question to that, from the Brighouse Elementary, which is in Richmond. So when they are going up to the space station, how many people typically are on one of those rockets? I know that there's been a couple different ones, but maybe talk about the different options of getting up to the space station.
Yeah, so it really varies how many people we're sending up, depending on what kind of mission objectives or science objectives that they want to accomplish. And it really is, they're very stringent about it because it is costly to send people up to space, up to the ISS and supplies. So they have to be very careful about when and how they send up people. And so if you take a look at recently, we had the SpaceX launch that went up to the ISS and that brought
Yeah.
Bob and Doug. So that was two people that got to go to the ISS on a different kind of spaceship that was launched by SpaceX. So Elon Musk founder of Tesla, rather than a Russian rocket, which we've been using so far since, or like for the past 11 years or so, I think. So that was the first time we launched from US soil.
Yeah, which was a bit different from like the space shuttle, which had could hold a few more astronauts, and it did look more like a plane. It looked really cool, but we have sort of streamlined. Of course, the space shuttle was very expensive to launch. It was very heavy, and as we've learned, through Newton's laws, and of course, like launching things into space, heavy things are going to need more fuel, and more fuel is more expensive. That's your basic Newton's law lesson right there. Final question. I guess we got more questions coming in from these students. We'll get to everyone's questions. Let's go off to Mars. So we did talk about Mars in opposition, and we are talking about humans going out into space right now, only to the space station. But what's it going to take to survive? Humans be able to survive if we were going to go to a place like Mars?
So Mars is kind of tricky because we think that in its past history, it might have looked something a little bit like Earth, but now it looks like a rocky, desolate red planet. And not only that, it doesn't have much of an atmosphere. It has an extremely ultra thin atmosphere, might as well not have an atmosphere at all. And of course, we know that we need an atmosphere to keep all of that nice oxygen here that we can breathe. And and then have things like greenhouse effects where we warm our planet a little bit. But because Mars doesn't have that atmosphere, it isn't able to do any of that. And not only do we need some way to breathe, maybe it's in the form of a backpack that has an oxygen tank, much like scuba divers going underwater. We also need water and food. And I don't know if the grade 5 class has seen The Martian, but Mark Watney in The Martian is a botanist who is able to grow food on Mars, and he does that using poop because poop has organic material in it. And so it'll be a little bit tricky for us to grow things on Mars without supplementing it with some other form of things like bacteria or microbes first.
What's really funny about doing these over Zoom is that that fact that you just gave, I can hear the groans of the students as if they're right here in the theater with me describing growing potatoes out of poop. Like, that's just gross. And it now gets me thinking, like, is it even worth it if we got to grow potatoes out of food? But I mean, if you need to survive, you need to survive, right?
It's true. It's true.
Let's now go even further off into space, because our second news story of this week was about black holes. So is a black hole not travelable due to the singularity? That's a pretty big question from someone in the grade 5 class. But let's talk about potentially being able to travel to a black hole.
Oh, as in going to a black hole, or
Yeah,
like flying by?
Well, it's probably playing into it,
Oh,
and then thinking about like the points, so the
sure.
singularity that it comes down into.
Sure. So a black hole is kind of a hard object to wrap your mind around. And in short, it is a hole, like a kind of like a pinpoint or a pinprick in the fabric of space-time. So if we imagine that space-time is a lower dimensional thing, so it's 2D, it looks like a really long sheet that extends out forever. And a black hole is if you took like kind of your finger and pushed the hole all the way down till it got to a point, a singularity at the bottom. That would be what a black hole is. And I would not be the first to volunteer to go fly by a black hole because of its immense gravitational pull and that experience of spaghettification, like your atoms being ripped apart, just like the star was devoured by the supermassive black hole.
Right. And of course, if you're going to watch The Martian, you might as well watch Interstellar and find all about what it may be like to travel close to a black hole. Another great sci-fi movie. Probably a little bit too advanced for the grade 5 class, but maybe in a few years. Let's follow up on that. So Harry's got a question about black holes, sticking with that subject. So black holes moving in the same direction and speed as the rest of a galaxy, or is there a special route pattern that the stars eventually get crossed by? So, like, I guess the question is, like, is the black hole rotating sort of like the same with the galaxy?
Oh, okay. So the deal about black holes is that they are the simplest objects in the universe. And that kind of seems like a weird sentence to say, but they're the simplest objects because we only need a few things to define what they are. And that's mass, charge, and angular momentum. So that's spin that Harry is talking about rotating with galaxies. And so because a black hole has such an immense gravitational effect, it does affect the spin or rotation of a galaxy, but that rotating effect is actually remnant from the formation. And we see that in a smaller analog in our solar system. When our solar system formed, we were a big cloud of gas, dust, and debris, and we started spinning around. And because we started spinning around, we started to flatten like a pancake. And the same thing is happening with galaxies as well.
There's so many food analogies now.
I know.
we started with spaghetti, then we went to potatoes, and now we're talking about pancakes. Pride says her 11-year-old wants to know, how cold is space? We did talk about it. It's really big and there's a lot of blackness to it. So just how cold are we talking here in space?
So if you are in the deepest, darkest place in the universe and there's nothing for, I don't know, billions of light years, you would be feeling a temperature of 2.73 Kelvin. And the reason why it's 2.73 Kelvin is because that's the temperature of the cosmic microwave background. So that relic radiation from the Big Bang, from the formation of our universe, that is the temperature or the base temperature of our universe. But let's say that you're on the ISS and you're going around the Earth, something like 23 times a day. If you're in the sun, then it'd be much hotter. If you're in the shadow, then it'd be much colder. So astronauts do experience a huge variety of temperatures, and it's very lucky that they have spacesuits to protect them from that.
No, Rachel, I was just looking at my weather app, and it's pretty cold here in the building at the Space Center. We're trying to heat it up, but I didn't see anything about kelvins on there. Could you maybe tell us what the difference between, because we use Celsius usually, but Kelvin is another unit of measurement for heat, right?
Exactly. Yeah. So it's another measurement of temperature. So there's Kelvin, there's Celsius, and there's Fahrenheit. Kelvin is particularly useful because it's defined based on 0 Kelvin being absolute zero. So things basically stopping motion in the classical sense. So they're not vibrating, they're not moving, and it's absolute zero. It's very, very cold. And it's kind of like,
how cold is absolute zero?
I think it's
Celsius.
negative 273 degrees Celsius. Yeah.
Go.
But it's like another way of defining a zero. Like we
Right.
define 0 degrees for Celsius as that transition point from water in liquid form to snow.
Yeah. So really, really cold is what you're saying.
Yes.
Another question from our class. Glad you guys could join us. Hopefully you join us every couple of weeks. This is a really cool one. So as far as we know, we do have humans in space. They have gone up there, but nobody has been born in space yet. But if there was somebody born in space, would that make them an alien?
I guess so. An extraterrestrial. They're outside of the Earth, I guess so, but I can't even imagine all the complications that would happen with trying to give birth in space. It's already complex enough on Earth.
Well, I mean, at some point, maybe, we would have to start to think about it, like if what would happen, and if the human species, did want to spend longer periods of time, but then I can always imagine. I can still imagine like the complications of just like, would you have a passport? Like would you, would it be like whatever country you landed in when you came back to Earth? That would be your country of origin. It seems like that would be a very complicated issue if you wanted to like live the rest of your life on Earth, but you were born in space.
Mm-hmm. The logistics alone are a nightmare.
But I guess that also relates to like if somebody was born like out on sea in the international waters. I've never actually thought about that. I should look that up to see how that works.
Yeah, I mean, I would assume that it's like the first place that they set foot on in a first country. Maybe that's where they get their passport. But what if you spend your entire life at sea? Then are you just not, you don't belong to any sort of country? I don't know.
Yeah, you're just a pirate at that point. One final question from the class, and then we're going to preview some of the exciting stuff that is coming up. So does a black hole count as a star?
Does a black hole count as a star? I would say no, because a black hole you can think of as an end state for a star. So there's a bunch of different end states. For example, our sun, it's a little bit smaller than all the other stars out there. And so it's going to end up as something called a white dwarf. But black holes, because they aren't made of matter, they're an absence of matter. They're a hole in the fabric of space-time. So they're not quite stars, and they don't generate their own light and, qualify for all the things that we would call a star.
but still really really cool, and of course like have lots of like light around them, but that's of course all the other stars around them, so the black hole itself not being a star. Okay, let's preview a couple of things we have coming up here, Rachel, because tonight we have a really great event. I know that you're really excited to talk to Dr. Tian Yu from the University of Oregon. We're going to be diving into one of the other big mysteries of the universe, and that is dark matter. What are some of the questions that you're really excited to get into?
I wanted to ask her about a recent paper that was published talking about a possible dark matter detection or dark matter signal for a dark matter particle. And it's kind of interesting because it's kind of a signal to pay attention to, but not a signal that tells us that a particle was for sure detected. Mm-hmm. So we want a value of something like 5 sigma. And so the Higgs boson, that's one of the force carriers for gravity, or a result of the Higgs field. That Higgs boson, that particle detected in like I want to say early 2000s, I can't quite remember, 2012, passed that test. And they were super sure that that was a particle. It's like something like 99.9999% confident that that is a particle. Okay. But with this detection, it's a little bit lower. So it's 3.5, so not quite 5. So I just want to ask her what she thinks about that and like where we're going to go with dark matter detection.
Yeah. No, that's a great question. I can't wait to get into that. So if you want to get in on this event, it's going to start at 7 o'clock Pacific time tonight. Make sure to go to our website to get tickets for that. And then next week, we're going to be live here on YouTube, and we're going to be talking about a really exciting event that's going to be happening, which is the OSIRIS-REx spacecraft, which we talked about when it first launched. But now it is there around Bennu, and it's going to do this tag. So what's going to happen next week, Rachel, with OSIRIS-REx?
So TAG stands for touch and go. And it's really exciting because it literally is going to touch and land for 5 seconds and then spit out a little bit of gas to kind of disturb all the material on the surface, and then take a sample and then get out of there. And so I think it's really exciting to be able to see a thing like OSIRIS-REx taking a physical sample from an asteroid.
Yeah, so there's going to be a bunch of things happening. So make sure to like and subscribe our channel here, because we're going to go live on Tuesdays when the actual event is going to be happening. Of course, but unfortunately, there's not like live cameras to watch it go live. But we will be talking about it on Tuesday. Wednesday, there's going to be a press conference to talk about some of the videos. So they will have some pictures and some videos that apparently they're going to release on Wednesday of next week, and then we'll come back and we'll talk about it. So to make sure that you're here with us, make sure to like and subscribe so you know exactly where we're going to be talking about that exciting mission. Okay, so much going on. Thank you so much to the Brick House Elementary kids that were here, of course, everyone out there. And make sure to go onto our website and look at all of the exciting things we have coming up. We have a couple of in-person events coming up. We have a home learners online event also coming up. So lots of exciting programs at the Space Center. Hope to see you there or in person. Until next time, and in a couple weeks. See you again, Rachel.
Bye.
Bye, everyone.